Yeah, hello everyone. It's our pleasure to have Sofiene to talk about his work on quantum machine learning beyond kernel methods. Yeah, I think this one is kind of impactful work because it's asked us to basically to look beyond kernel methods and trying to see what other things quantum machine learning could offer us. Yeah. So Sofiene, so now the floor is yours. You can maybe start your presentation.
Thank you, Vinny, for the presentation introduction. So yeah, as Vinny said, I will be telling you about our work, quantum machine learning beyond kernel methods. So this work was done in collaboration between people in the University of Innsbruck, where I'm currently doing my PhD, finishing my PhD actually, but also the University of Leiden in the Netherlands and the Max Planck Institute for Intelligent Systems in Tübingen. So this work got recently published, but there was a version archive for more than a year now. So, but if you're familiar already with that version, you may be worth it to check the published version. We have also new results there. So, and also I'll be telling you about these new results in this presentation. So let's start. So I won't give too much motivation for why we do quantum machine learning, unfortunately. I hope this audience is already familiar with that motivation. I will start straight from the meat. I will just tell you that the quantum machine learnings we look at are essentially parametrized quantum circuits. These are essentially just quantum circuits where some of the gates used in the circuits are used to encode data. Some others are used to as foundational gates. And this circuit is essentially used to compute a function that is used in machine learning. And while there are various names for such models, like called parametrized quantum circuits, variational quantum circuits, quantum neural networks, they usually all mean something similar to this. But when you look closely as well, you notice that there are various models that are used depending on how the data is encoded, how the function is generated, things like this. These little subtleties that may make it look a bit hard to understand how or where should you use one model or the other. And that's a bit what I try to decipher in this talk. And also these quantum machine learning models, they've been applied to basically most of all machine learning applications, supervised learning, unsupervised learning, and reinforcement learning as well. But in this talk, I will focus mostly on supervised learning. And I mean, yeah, I will just in a few slides give you some very textbook stuff about supervised learning, but this will be actually very important for the rest of the discussion. So yeah, what is a supervised learning task? Is basically we are giving a data set of training samples, x1 to xm, and their labels, which are labeled by a function that is unknown. J is usually unknown. We only have access to these examples, and we try to fit the function j on the entire data space out of these few examples that we're given. And we distinguish, of course, two types of task, and this will depend essentially whether the labels are discrete or continuous. In the case where the labels are discrete, we talk about classification. In this case, you just have to classify spam from non-spam emails. And when these labels are continuous, we'll talk about regression. You just have to feed a function essentially as a function of its input. Right? We also can distinguish very easily between linearly separable and non-linearly separable tasks. So in the case of classification, for instance, this task of distinguishing between spam and non-spam, this very simple toy task that you see here, can clearly be linearly separable. What we mean by that is that this separator here, this function that separates spam from non-spam, can be modeled by a linear function in this feature space, in the space of data, which means that for data vector x that describes this email, we only need to look at its inner product with another vector in the same space, and this function actually, this inner product between the two, or more precisely its sign, will tell us if it's positive or negative, will tell us whether we're looking at spam or not. So that's what we call a linearly separable task. Non-linearly separable tasks are tasks where we cannot find such a linear function that perfectly separates the data in data space. So in this case, whatever hyperplane you will take in your data space, you will never be able to separate blue from red dots. So what is the solution for this problem? The solution is essentially to not work in data space where things are not linearly separable, but to work in feature space. What we mean by that is that we take our data points and we apply a nonlinear function to them. In this case, it's just x1, x2, x1 plus x2 squared, which is a nonlinear function, which we essentially add this new dimension to the feature space, where now it becomes, the data becomes linearly separable. So now in feature space, this H is now not data space, but feature space, the data becomes linearly separable. We can find a linear function that perfectly separates blue from white points in this example. But the question remains is, how do we find these, so as I told you, this linear functions is defined essentially by, after we've defined the feature encoding, it's defined by a weight vector that we take the inner product with the feature vectors with. And the question remains is, how do we find this hyperplane W that perfectly separates the data points? So visually here we have 3 dimensions, so it's quite simple to see that, yeah, it's essentially this hyperplane that cuts the data like this. But imagine a very high dimensional feature space, like we talk about millions of features, for instance. This becomes a bit harder task. And that's essentially where kernel methods can come in handy. So as a reminder, this is the task we're looking at. We have a data set of m data points. And the idea of kernel methods is to say that our weight vector that we take in this feature space is, we take it to be spanned by all the data points in our data set encoded into feature space. So these phi of xm are essentially all the data points in our data set that have been encoded in feature space. And our weight vector now, we say we're restricted to be only a linear in all these encoded, linear combination of all these encoded data points, right? So what does the resulting model look like? It's essentially now we plug in this expression for W. So by linearity of the inner product, we can take out this sum and weights, and we end up with essentially this inner product between an input X and all points in the data set. And this is essentially what we call our kernel. Our kernel is essentially a function that takes as input 2 points in data space and then maps it to feature space and computes the inner product. And this can be done even implicitly. You don't even have to do it explicitly in some cases. But yeah. And now the very interesting property is that finding these alpha m's, these optimal alpha m's that perfectly separate our training data can be done very efficiently by just essentially computing this kernel function for every pair of points in our training data. So how do we do this? Essentially, we take all our points, all pairs of points in the training data. We compute this kernel matrix now. It's a size m by m matrix. And then finding this alpha m becomes a convex optimization problem, where essentially we just have to invert somehow this kernel matrix, and we get the best alpha m's that perfectly separate our training data or perfectly fit our training data. And that's essentially the very cool feature of kernel methods. Yeah, so Benny, I don't know if I want to remind people that if there are any questions, please feel free to interrupt me. I will do some checkpoints during the presentation. So is there any question at this point? Okay, everyone is well rehearsed in kernel methods, I see. So
yeah, so far I didn't see any questions coming from the chat, so I guess you can proceed on.
Thanks.
Yeah.
Okay, so these what are kernel methods. Now let's put some quantum into it. So the different quantum models we consider, the first one is essentially an explicit quantum model. What we mean by that is that we take a quantum circuit, we initialize the input in an all zero state, let's say, and then the first part of the circuit, all the first gates that appear there, only depend on the data. They don't have any variational parameters. They're only used to encode data in the quantum in this quantum state. And then after that, in the second stage, we do a variational processing where all our gates are now variational. They don't depend on the data anymore. And then we measure the expectation value of some observable. And this is how we get our label of our point X that have been encoded here. So yeah, if we put some math into it, we call our feature vectors phi of X, which are just the unitary evolution u phi of X of of the all zero state. And then if you look at the model that the resulting model that we get out, the function of x is essentially the inner product between this psi of x, sorry, and the observable O that have been evolved under this unitary d of theta, right? This diagram actually should be on the other side, but it doesn't matter. So really, when you look at the expectation value of this O under this quantum state, is also essentially equivalent to looking into the expectation value of this rho of x, this feature encoding, with an observable O that has been evolved under v theta, right? This is the Hilbert picture of this expectation value essentially. And from here, you can actually notice that you clearly have a linear model in rho of x, right? So when you look at the expression we had for a linear model, it's just the phi of x taken as an inner product with a weight w. In this case, our phi of x is the density matrix rho of x that represents this quantum state, and our weight vector w is just the O theta matrix, the Hermitian observable O theta that we take as inner product with rho of x. So this is clearly a linear model in feature space. Our feature space is now the Hilbert space of this quantum state. And on top of this, because our O theta does not span all possible Hermitian observables, it's actually limited by the eigenvalues of the observable O and by the variational processing v theta of this variational circuit. Then essentially we only have access to some manifold inside the space of all Hermitian operators O theta. And that's why we say this is a linear model with a restricted W. We don't have access to all possible weight vectors for this linear model. On the other hand, so the same people that first noticed this connection to linear models, so these first two papers here, also noticed that since you have a linear model, you can also turn it into a kernel model, right? Where essentially now, as we did before in the previous slide, we take our weight vector W, or our observable here O, to be a span, a linear combination of encoded data points from our data set, right? So this is exactly the same thing that I did in the previous slide. And now the resulting model is a kernel model, is a kernel linear model, where the kernel function, right, the inner products between encoded data points, is essentially can be computed with a quantum circuit that looks like this. So we said that our feature vectors are this quantum state psi of x. So essentially now, if you take the unitary U that generates psi of x, you take it in reverse, but with x prime, and you measure the expectation value of an all zero state at the output, what you're essentially measuring here is the inner product between the rho of x and the rho of x prime, right? So that's how you get an evaluation of the kernel, the quantum kernel of this model, right? And then your implicit model is just a linear combination of this kernel function evaluated for an input x and all data points in your data set. But a third model that had been introduced in the literature is somehow a generalization of this explicit model, where we now don't only have one encoding layer and one variational processing plus measurement, but we have an alternation between encoding, variational processing, encoding, variational processing, where all these layers are allowed to be different, right? So U1 and U2 here can be different, V1 and V2 can be different, but it's actually a very general way of defining a parametrized quantum circuit for machine learning, right? It has a lot of freedom. And of course, this is seen as a generalization of this model, since when you restrict to only having 2 layers in this model, you recover again the explicit model, right? But what we lose, of course, is also that now we don't have a linear model anymore, since we can never find the feature encoding. By looking at this picture, we can never really see a feature encoding that encodes the data, a quantum state that encodes data, and everything else is data dependent. If you stop here, for instance, this still is data dependent. If you stop at the end, you still have variational processing in your encoding. So really, there is no reconciliation with the linear model picture at this point. So if you want to visualize these 3 models in a Venn diagram, you can see linear models include explicit and implicit models, right? And then data reuploading seems like a generalization of these explicit models. And now the questions that we address are essentially, is there a unifying formulation for all these models, right? We would like to include everything in the same circle, let's say. And the second question is, how do these models compare in terms of learning performance and resource requirements, right? Is there any advantage of using a data reproducing model versus an explicit model? Is there any advantage of using an explicit model versus an implicit model? That's the questions we try to address, right?
Sofiene, I have a question over
Yep.
here. So
Yep.
the data over there, like in the circuit for C, could be different,
Yep.
right? Over here, you just like note that they are the same just for simplicity, right?
Yeah.
And
So
the
for
other,
simplicity, yeah. For simplicity, we put X to be our entire data vector. And then, of course, this unitary can only use a subset of the data vector, right? So in that sense, the data that is used in this unitary and the one used here can be very different.
Yeah. And the other question that I have over here is that why couldn't we just like combine all the like trainable block and the encoding block together and treat it as a feature vectors? And like for example, we can use the like kernel target alignment to get the best data and treat it as a kernel method, and this will allow us to separate like put it into a kernel form, right?
So I'm not sure what the first part of your question really means. You want to combine all these U's together?
Yeah, so basically we have row X of data, right? And then this will be our feature maps. And yeah. So like so over the all data over there, you basically group VL to the observables, right? Could we just put VL to the row as well? And then row will be independent of data and treat the row of X and data as the feature maps.
Sure. Okay, I understand now. Well, the thing is, you don't really recover a linear model how it's properly defined in the literature, which is a fixed encoding, a feature encoding of the data, and taken as an inner product with some data independent vector, right, in the same feature space. So that's the proper definition of a linear model, and you kind of lose it here the moment you start making this feature encoding variation, right? The moment you put parameters in your feature encoding, you lose kind of the proper definition of a linear model. Of course, one can also use kernel target alignment or kernel tangent
target alignment.
Yeah, exactly. Or methods like this, but they're not really using properly the linear model literature anymore, right? So they somehow kind of oscillate between updating the encoding, then doing some optimization of the linear model, then updating the encoding again. This is kind of a hybrid model that is not really a proper linear model as is defined in literature. And this is really what we want to end up with, somehow to end up in a proper linear model where you have a fixed encoding and a general weight vector that takes inner product with it. And really a separation between encoding and variational processing or weight vectors, right? Which otherwise you won't get.
Okay.
Any other questions? Okay.
Yep. So far, that's fine for now.
Okay. So now we essentially try to address these questions one by one. We start by the first question. Is there a unifying formulation for all these three models that we introduced? And the answer turned out to be yes. And what we prove is that if you take a data reuploading model, so essentially you look at you fixed your variational circuit that define and your observable that define your data reuploading model. Now, if you give me that as input and you look at all possible functions that this thing can represent, I can find a mapping that will give me an explicit model that represents all these functions in this original family exactly. That means for all assignments of x and theta, we have exactly the same functions, function values, right? Which seems a bit surprising at first hand. And actually, it turns out that such a mapping from data reuploading to an explicit model is impossible by preserving the size of the Hilbert space or the number of qubits on which these circuits act. So essentially, we're not just trying to commute U2 with V1 and U3 with V2 and V1. We're not just trying to commute through the unitaries to the beginning and the variational unitaries to the end. This is not possible, right? What we do is something a bit more tricky where we add more qubits And this allows us to essentially do a feature encoding and a variational processing that are at the end equivalent to having a data recording circuit. And this I will describe in detail in the next few slides. And what we show really is that, I will get to this result as well, is that really it is impossible to do it with preserving the Hilbert space dimension in general. So we have essentially a lower bound that tells us this is not possible in general. But yeah, it's possible by enlarging the number of qubits. Okay, so this is what we're getting at. We're trying to get at a mapping that takes a data replotting circuit at the input and outputs an explicit circuit. So let's do this. Let's start with a very simple approximate mapping. So before I promised you that there would be an equality here, but let's first start with a very simple mapping that gives us an approximate equality, an approximation. And this will actually be gives us a lot of intuition of why the exact mapping works. So let's start with the data replotting circuit, where we consider our input X to be a d-dimensional real valued input. And we want to end up in explicit mode. And what do? So we look at all encoding gates that are in this circuit, in this data replotting circuit, and they're essentially just rotations. So all encoding gates can be expressed as a general rotation of single qubit, but multi-qubit rotation. So an evolution of a certain Hamiltonian that can act on all the qubits and parameterized by one of the inputs X, right? So this is the general form of the encoding gate that we look at. And what we do is we essentially transform it in this manner. We use this gadget where instead of doing the rotation directly, we essentially encode the X in an additional qubits, and we encode it in binary form. For instance, let's say our X has this binary representation where this B0 to B3 are bits, right? It can be infinite, of course, but we stop at a certain finite precision. And then instead of doing the rotation by encoding X directly, what we do is essentially we do a bunch of controlled rotations where we first rotate by 1/2, then we rotate by 1/4, then we rotate by 1/8, 1/16. And we only rotate by 1/2 when this first bit of the representation is 1. When it's not, we don't. Then the second 1/4 rotation, we only do it when the second bit is 1, otherwise we don't. And at the end, what we end up with here is an approximation of this original rotation, right? If you do it at infinite precision, of course, you will get exactly the same thing. But because we stop at a certain precision, what we end up effectively, what happens on this qubit is a rotation to finite precision, and that approximates this original rotation, right? But what's the cool thing about this gadget is now all these gray boxes are completely data independent. Like if you don't see what's in these registers, if you don't know what is in these registers, the operations that you do here essentially won't change, right? You always do a controlled rotation, no matter what the values are here, right? But these values now, these values of these qubits is what encodes the data in our circuit. It's eventually a bunch of X rotation on the on zero state that will encode the data X on this register essentially. And now what we can do is that if we put this encoding on these extra qubits first, and then all these data independent rotations later in the circuit when we need them to encode the data in the working qubits, what we end up is this part of the circuit becomes completely data independent, right? There's just controlled rotations plus variational operations and stuff like this, whereas this part of the circuit is now just taking care of the encoding, right? Where now we effectively get an explicit model where the feature encoding is essentially just this bit string encoding of the data on ancillary qubits, right? And at the end of the circuit, what we do is we just discard that information and we just look at the expectation value of our original observable on this working qubit. And what we see is that the function that we get out of this is a very good approximation of the original function. And this approximation gets better and better depending on the precision of our encoding, right? So the better the precision that we get, the better that we put, the better the approximation of that function gets, which kind of makes sense, right? Any questions regarding this mapping?
Is there any optimal cutoff that you kind of suggest, like for this kind of approximation? Because
optimal cutoff.
Yeah, as in so we just like choose the precision depending on how much that we want the approximate functions approximate
exactly.
the function.
Yeah.
Okay.
Yeah, and you can actually relate this precision very well to the this approximation error to the precision of encoding that you put here. And this we do in the paper. We actually show how these things, the two things are related, right? You can bound these things.
Yeah, so could you like kind of like briefly mention like what is the scaling dependence between like theta and epsilon?
Okay.
Is it like
so
epsilon square or?
Yeah. All I remember is that you need essentially something that scales logarithmically, like the number of qubits that you need here scales logarithmically in this error delta divided by the number of encoding, number of angles that you encode this way.
Yeah,
something like this.
The scaling is quite wild then. Yeah, because it's
it doesn't really kill you, right? It's not that bad. It actually very much looks like the scaling I have on the next slide for the exact mapping. So it's very similar scalings, which actually turned out not to be very surprising. But yeah, I will get to the scaling on the next slide, and then.
Yep, sure. Looking forward for that. Thanks.
Yeah. Any other question? Is it clear what we're doing here? Okay.
Seems like everyone's clear.
Okay, good. Okay, if you feel a bit cheated, that's a bit normal. Now we also felt with this mapping. The next mapping is actually a bit more interesting because we also get exact function representation, which is actually pretty cool. And so, yeah, this is the exact mapping we end up with. It looks very similar in the sense where we end up with controlled operations that act between the working qubits and these ancilla qubits. And the data will be encoded very simply in like tensor product quantum states, feature states. And so this is essentially what we're using now for the exact mapping is some gate teleportation gadget. And if you're, you don't have to be very familiar with what gate teleportation actually works in practice, but in this case, this is the idea of what we do. Imagine we want to implement a rotation RZ of X on some state psi, right? Instead of directly applying RZ of X on psi, what we can do is use an ancilla qubit. Now, just look at these first two lines. We use an ancilla qubit initializing the plus state, apply this RZ gate on it. And now, if we apply a C naught like this, you see that if you do the math, you see that if you now project this qubit on the 0 state, what you effectively have done is apply this RZ gate on psi. What you see is really that you apply this RZ gate on psi. The phase propagates and then you get the RZ gate on psi. But if you get a projection on the 1 state, right? In that case, what you get on this qubit is an RZ minus X. So it's minus the angle that you want. There's a minus angle that hurts you. And that's why gate teleportation usually what it does a correction on the target qubit to correct for this minus sign when you get a 1 outcome here, right? But this 1 outcome also happens with half probability, right? So with half probability, you will get what you wanted, so the exact RZX gate on the psi, and with half probability, you get RZ minus X. But instead of correcting, because correcting involves data-dependent operations on this state here, we don't want that. Instead, what we do is we apply gate teleportation again when that gate teleportation, the first one, was faulty. Essentially, when this one gets projected into a 1, instead of projecting, what we do is we control on getting a 1 here as well. And we apply a gate teleportation of RZ 2x. So we had a minus x to correct for. By applying a 2x, we get back to an RZX, right? So we teleport again this correction here. And now the total probability of error is not 1/2, but 1/4. So we divide by 2 a probability of error. And now essentially we can repeat this again. And instead of applying the correction RZ4x, we gate teleport it, right? And now probability of error is 1/8. And we can continue so on and so forth. And we can essentially reduce exponentially the probability of error by adding more and more gate teleportations, such that at the end, what we care about is that none of these qubits here that we use for gate teleportation gives us a 1, right? And so this essentially, and this will happen with probability that is exponentially small. So we only have to post-select, right, on a 1 minus an exponentially small probability of happening. So it's a very large probability of happening. So we only have to do a projection and a post-select on something that happens with very high probability. And the very cool thing is that post-selection with very high probability is not a problem in our model, right? We have full control over the observable that we put in here, and we can very well add projectors to this observable, right? And since essentially our post-selection happens with very high probability, we get the right outcome, we have a very high probability of success, the reweighting of our model such that we get the right functions, the right expectation values, is by a very controllable success probability that we can get arbitrarily close to 1. Okay, so maybe this is a bit hand wavy, but the idea is that we kind of replace the error of approximation by just doing this bit string encoding by an probability of error of gate teleportation, right? And this probability of error can be made arbitrarily small by doing this nested gate teleportation, right? And such that the reweighting factor that we have to put in our model can be made arbitrarily close to 1, right? So we don't have too much loss in terms of the number of shots that we need to run this circuit in order to get the same function, right? So we get equality in terms of the bubbles, and we just get a small overhead in the number of shots that we need to do in order to correct for this this post-selection that happens here. Is it a bit clear?
Yeah. So actually for this one, right, when I like so this one is there's one kind of interesting things that going into my head is that this seems to be a protocol for like cloud quantum machine learning, right? You can put one data at one place and then the processing unit at the other place, and then you just use the like the entanglements, and then you can just use teleport the data to the other end. And do
that's actually very cool.
right? Yeah.
Yeah, definitely. I mean, technically, you wouldn't really need to know what's happening here, right? You could somehow kind of entangle together your working qubits with other qubits, data qubits, right? So yeah, it definitely could have other interesting.
Yeah, this one's I would say like all those people that cares about privacy will definitely love your algorithm, right? Yeah.
Definitely.
Yeah, and it seems to me that this is the first kind of measurement-based first kind of like quantum machine learning algorithm that is tailored for measurement-based quantum computers, right?
Exactly, yes. So exactly, that's exactly it, right? I mean, measurement-based quantum computing is linked to blind quantum computing. So at the end, it's not very surprising that also this allows for some privacy. Okay. Yeah, right. So trying to link this further to privacy issues in machine learning, I think that would be a very cool direction. Yeah, definitely. I haven't thought too much about it at this point.
Yeah, okay. Yeah. Thanks.
Sure. Yeah, I can also, if there are other questions, I can also be happy to reply.
Yep. So far, I didn't see any question coming from the audience.
Okay, so then we can just move on. Yeah, and this is the scaling that I wanted to give you at the end. If we had D encoding gates in the circuit, right? The number of qubits total qubits that we need here scales as D log D, and this should be divided by delta, where delta is essentially the probability of success, and this can be made arbitrarily close to probability of failure, sorry, and this can be maybe arbitrarily close to 0. So it scales as D log D over delta, right? So that's the scaling that we get, which turned out to be efficient. If you forget about the delta, it's essentially a D log D, where D is a number of encoding gates.
Sorry, actually, I have another question over here. Seems like this kind of structure that allows you to use the quantum circuit cutting technique to simplify the your circuits, right? As in, like
if you want to use circuit cutting.
Yeah, basically like now I know about algorithms that like IBM trying to use to combine between like two superconducting chips, right? Is by doing quantum circuit cuttings where you do measurements in the mid circuits, and then you get some probabilities, right? Get some result out, and then you prepare the state to feed forward to the next one. Yeah, and then it seems like you can do the same things over here as well. And you will reduce basically the size of basically it will reduce the requirements of your system size quite significantly if you be able to exploit some structures of that.
But how do you see that this is more advantageous for that?
So for though that technique is basically trying to trade the space with the number of repetitions on the measure on the experiment, because like if you do probabilistic measurements in the meters, right, and then you have to do a lot of it. It's quite hard to describe using this diagram, but they have a pretty simple kind of quantum circuit to illustrate that ideas. Basically, it's just that, okay, you can find, like, for example, you have 2 qubits or 3 qubits, right? And then you entangle first one to the second one, first one to the third one, right? And then what you can do to separate it into like two qubits circuit is by doing the measurement after the first CNOT gate. Yeah. So after you measure the first CNOT gate, then you get some measurements, right? Yeah, because the first qubit is like entangled with the third one, but not with but the second one is not with the third one, right? You can separate it out, and then based on the measurements, you can prepare the state, and then trying to do and entangle the state with the third qubit. Once you get all the statistics, then you can combine all the statistics post-processingly. Yeah.
Yeah. Okay.
Yeah, but of course, like it relies like the more qubits that you entangle with one another, the more measurement that you have to do. But then it seems like over here you could get rid with some of it with the structure that you have in your circuit.
Okay.
Yeah, I'm not too sure how that will work, because have to look like how your circuit will be looked like and how the protocol will be applied on that. But it seems like you can break down your circuit into smaller pieces and then do everything like individually, and then compile the statistics afterwards.
Okay. So, yeah, I don't totally see it at the moment, but I mean,
just
nice
some kind of like thing that pop up in my mind. It might not be working, but just just saying.
Sure. Yeah, that would be interesting to look into.
Okay. Yep. Sorry. I think you can go ahead.
Yeah. No. Okay. So this was the first part where we showed essentially the exact mappings between data recording and explicit models. And of course, these mappings are not unique. We just presented one, and it has this overhead in the number of qubits that is d log d essentially. And now, the second question that we want to address is, how do these models compare in terms of learning performance and resource requirements? And this is essentially where the title of the talk in the paper will actually resonate. And so let's get back to these kernel methods, right? So again, we have a data set in our task, and how we train our kernel model, or our model in general, is essentially just by looking at the performance on the data set, right? That's the only thing we have access to the target function. So we simply take an empirical loss or training error that is essentially just looking at how the model is doing on the training data, right? And the representative theorem, which is a very powerful tool, tells us that essentially in the space of all linear models with this fixed feature encoding. So now if you have all this, where you fix your feature encoding and you look at all possible linear models you can get, well, in this space, the function that is minimizing the empirical loss, so the loss with respect to the training data, is essentially of the form of a kernel model, right? The weight vector is a linear combination of encoded data points, right? And recover again the same expression that I gave you before with this kernel function applied on all training data with an input x weighted by an alpha n. The representative theorem takes that this function is going to be minimizing the empirical loss. And we know how to find the alpha m's efficiently, as I told you before. It's just a convex optimization problem. So what this representative theorem seems to suggest is that implicit models always have a lower empirical loss than explicit models. They will be outperforming any explicit model, because the explicit model also live in the same family of linear models, but they may look at very different weights, parts of the weight space, right? And therefore, why would you look there if you know that this the model that minimizes empirical loss is of the form of the kernel? And by the way, this representative theorem also works when you add regularization. So if you add regularization term to your empirical loss, which is somehow used as a heuristic to prevent overfitting and things like this, still the representative theorem guarantees that the function minimizing the empirical loss with regularization will be a kernel. So it's actually a very powerful theorem, right? And now, what you learn about representative theorem is that implicit models should always outperform explicit models. Turned out to be not really true, right? I mean, this kind of observation is also what justified titles like this in Hilbert. All of quantum machine learning should be kernel models. Why would you care about explicit models, right? But turns out to be like, here's a very simple example of an explicit model outperforming an implicit model. Let's take, for instance, the results of our approximate mapping that we had before. So as I told you, this kind of circuit can represent basically a good approximation of any data recoding circuit. It can really represent very non-trivial functions, right? And now let's look at the kernels that result from this feature encoding, right? So the feature encoding is just the bit strings on the Sincilla qubits and 0 states on these working qubits. Now, if you look at the kernel model is just the inner product between these two quantum states for input x and input x prime, right? And what you see is essentially, this is the canonical delta between the bit strings that encode x and the bit strings that encode x prime, right? And now any implicit model resulting from this kernel is just going to look as the linear combinations of this canonical delta between the input x encoded in bit string and the data points x, m in our data set. So this thing essentially will have no generalization whatsoever, right? Anything that is epsilon away from any training data that we have, right, where the epsilon depends on the precision of your encoding here, will have an inner product 0 with all your data set, and will perform very badly, right? It will give you a 0. The function will give you a 0 essentially. So it will not generalize at all beyond your training data. And remember that the functions that we can represent with this type of circuit are essentially very large. It's essentially any data recording circuit to good precision, right? So you kind of see the gap, right? The explicit model can represent very arbitrary functions, whereas the corresponding implicit model here will just represent canonical deltas. Right, so what did we miss? Well, essentially is that the empirical loss is not the true figure of merit. The true figure of merit in machine learning is expected loss. It's how our model performs in the entire data space. And the representative theorem does not give you any guarantee on how the models will perform, the kernel models will perform on this expected loss, right? And what we see is essentially that things can very well overfit. And if you look into the space of all linear models, right, the kernel models essentially implicitly have access to the entire space of function that is representable by a certain feature encoding. This is called the RQHS. This is the space of all possible functions that can be represented as with a fixed feature encoding. And the implicit model will have access to all that, and it will select a certain function that minimizes the empirical loss, right? But this function, as we saw in the previous slide, can be very much overfitting. Whereas, and then the explicit model in this entire RQHS, as I told you, it will represent only can be very small manifold or very interesting manifold of functions, such that if you do the optimization of that manifold of functions, the minimum that you will find, the minimum of the training loss that you will find, may be a very interesting function, right? That the RQHS has access to, but it will ignore it because it can very much overfit on the training data, and that's better with respect to the training loss, right? So this is kind of the advantage, pictorially, of the advantage of an explicit model. This restriction on the weight vectors that we have access to in a linear model can be a very useful tool to avoid overfitting, to generalize well, to represent very non-trivial functions, right? And pictorially, that's essentially how you see kind of an advantage of explicit model. And to illustrate this numerically, we just conducted an experiment related to this Power of Data and Quantum Machine Learning paper, 2021. And essentially, we took in this paper, they do a numerical experiment where they take data from the fashion and NISQ dataset, which are 28 by 28 pixel images. They do a PCA, a dimensional reduction, and then they encode the data into a quantum circuit. And then with some choice of variational processing, they generate new labels for the data. So the data that is used here is just the data distribution, really, like how the X's are distributed. And the labels are now generated by a variational quantum circuit. So these are the labels of our training class. So we do a very similar thing. We just encode our data into some variational circuit, explicit variational circuit, and generate new labels for the data for some assignment of parameters theta. And if you look at how this looks like, it looks something like this. And then what, similar to what has been done in this paper, we essentially compare the performance of an implicit model using the same feature encoding as the one generating the labels to a bunch of classical models. So neural networks, SVMs, a bunch of classical models. We just compare the learning performance of these things in learning this target function. But additionally, what wasn't not done in this paper, we also compare the performance of an explicit model that not only uses the same feature encoding, but also uses the same variational processing, but initialized in a different part of the space. Of course, we randomly initialize the parameters again, right? So we compare these three classes of models and see what we observe. And this is what we observe, where blue is essentially the classical models, the best classical model, sorry. The red is what the implicit model does, and the explicit model is represented in blue. And what you can see, the observations that was done in Google is that classical model can indeed perform as well, in some regimes, can perform as well as the implicit model, right? So N here is just the number of qubits that we use, that we've used in our dimensional reduction. And we look essentially as system size grows, how the performance of these things do. And the lower, the better, of course. We try to get to minimize the error. And what you see is that for this regime, 7 and above, blue and red are doing essentially a similar performance in testing error, right? But what's not noticed in that paper is that explicit models can very well outperform both of these two things, right? So it's not sufficient to say that the implicit model will basically do as well as classical models, and then why should we use a quantum model in the first place? We should also look at the explicit model, because in this case, they actually perform way better, right? And now the observation that we made before about training versus testing, also you can also observe in this numerical experiment. As you see, the red dotted lines here, which represent the training error of the implicit model, is always very close to 0, right? But what you see is that the testing error really jumps off the roof at a certain point. And yeah, the model is actually overfitting on the data. Whereas an explicit model will have a training error and a testing error that both stay close to each other. And in this regime, it will actually perform way better than both implicit and classical models, right? So, okay, the numerical experiment is a bit contrived, but it's just a proof of principle to showcase what we wanted to say before about these caches of the representative theorem, about training versus explicit training versus testing error. Okay. So
sorry, I have one question. Like,
yeah.
So what's the gray areas means over here? Is it the standard deviation or something like that?
Yeah, it's standard deviation. So we do essentially 10 random initializations of each of the models. So you got it? Yeah, no, it's 10 different labeling functions. Yeah, that's what it is. It's we have essentially 10 labeling functions that are generated as such, right, for different parameters of the variational circuit here. And then this is essentially the average performance over these 10 labeling functions, right? And the standard deviations is in the gray area.
Yeah, and like for the implicit model, do you know why there's a peak like between 4 to 7, like 8 qubits?
Yeah, it seems this has to do with it seems to be linked a bit to barren plateaus, and so the explicit model becomes hard to train in this regime for some
But
reason.
not
And
for more than 9 qubits?
yeah, this has to do with the way we also the depth of this variational circuit that we use here, and yeah, it's really
I
related
remember
to
you kind of like trying to keep the parameters constant. So like when you have
exactly, yeah.
most side, then you have deeper circuits for that, right? If I'm
Yeah,
not wrong.
we were trying to get something that is non-trivial. So a trivial result would be if you had a variational processing that is just very simple and very shallow. In that case, essentially, it would be simple for all system sizes for the explicit model to learn something interesting. So what we try to do instead is try to look into a more interesting regime, which was keeping the number of parameters constant at all sizes, which means that at larger sizes, the circuit gets a bit shallower, and at smaller sizes, it gets a bit deeper. So here it's very deep, here it's very shallow. So it's quite easy for it to learn something here. It doesn't have that much barren plateaus. Here, because the system size is small, a deep circuit is also not a big problem. And this regime here is essentially kind of an intermediate thing where training becomes a bit harder for the explicit model and it kind of struggles. But the important thing is that even in this regime where it's not so hard for the explicit model to learn, it should also be easy for the implicit model, but actually it's not. The implicit model performs very badly, right? Okay. So that's essentially what we want to showcase.
Yeah,
like there is
actually,
a regime.
yeah, actually for this one, this observation, my current work seems to have some explanation on that, but we can keep it for later on.
Yeah. Okay, that would be cool.
So for this one, so for the number of like parameter that you fix is also for the trial function that you like the target function, target function.
Yeah.
Okay.
Yes,
okay.
yes. So they have the same number of parameters.
Yeah, we do have one question here. Is numerical results means that explicit quantum models, non-kernel methods has better performance compared with implicit kernel methods? Yeah, basically, essentially, he just trying to ask like whether the explicit model can outperform the implicit one, like based on the numerical result, and like if it, like the answer is yes, right? I guess like from the
explicit
training,
yes can outperform, right? Yeah. From what you see here, the explicit can really outperform the implicit
in terms of testing results. Yeah, because for
testing error, exactly.
Yeah,
the training error will not be, but the testing error, yes, right? The generalization performance will always be better. But yeah, as you can see, the dotted red is always below the green dotted, right?
Have you looked? Yeah, just a question here. Have you looked into the generalizations error for kernel methods? Because I know for the generalization is double bounded by the trace of the kernel, something like that. And for different kernels, you have different complexities of the models. Have you ever like look into it? Look into that to like see to find some possible explanation on the performance that you shown here.
Yeah, we haven't really explored that.
Okay. Yeah, we can talk about that.
Probably you could also find a good explanation in terms of the kernel that actually is there.
Okay. Yeah.
But yeah, we didn't really look into it.
Okay.
Okay. So these are numerical experiments. Of course, you may have doubts at this point why this is so contrived. And can we find a simpler argument for why explicit model can perform better? And we actually give some theoretical results, some rigorous theoretical results on why there is actually a separation between these different models. And moreover, we even show that there is a separation between explicit and data reproducing, which is actually quite cool. So essentially what we end up showing, this is the result, is that there exists a regression task where let's say X is the input, right? And it has a dimension D, it's a D-dimensional vector, such that we see a separation between all three models that we consider here in terms of the resources requirements that they have in order to solve this task or to have a non-trivial performance in this task. And what we see is that the different resources that we look at is a number of qubits that these models must use and the number of data points that they must use as well to have a non-trivial performance. And what we see is really exponential separations, or double exponential in this case, between implicit and explicit in terms of data points, and a D versus constant separation between explicit and data recording modes. So this kind of gives us a hierarchy of the resources needed between these different modes in order to solve this task, which is actually quite cool. And the learning task we're looking at is essentially that of learning parity functions. So parity functions are very much liked in complexity theory. They have a lot of interesting properties, and they also like to, they're also interesting to showing separations between different modes. For instance, this paper that we're really inspired by shows a separation between neural networks and classical linear models. So it's very much, our result is very much inspired from there. It's just put in the context of quantum machine learning and show interesting results there. So the parity functions we look at, they essentially take as input a d-dimensional bit string, say plus or minus 1, dimension d, and the labels are plus and minus 1. And the different functions we look at is essentially these parities, which are obtained as the product of a subset of this entire input bit string. So A here will define a certain subset of marked elements in the bit string, and the function is simply the product of these elements, right? So in this case, it's plus 1. Multiply these orange things, and A, right, in our entire concept class, all possible functions we look at, A can essentially be any assignment of any subset of this entire bit string. So how many A's do we have is 2 to the D, right? That's all possible A's we look at, all possible functions. So this is the concept that we look at. And what we want to try to understand is the resources that the model needs in order to have a good performance over all possible labeling functions, right? So then we want something that a model that should be able to learn all possible functions for labeling functions for all possible A's. Okay, so the idea pictorially to show the separation is very nice and very pictorial. So let's look at the space of all possible functions that go from this hypercube plus and minus to the D to the real values. So this this space of all functions has a very nice basis, which is the basis of all parity functions. Right? What you can show is that all parity functions are orthogonal in space, and therefore they form a basis of all functions that go plus or minus 1 to the D to the real values. And as I told you, how many parity functions do we have is 2 to the D, right? How many subsets we can select is 2 to the D, and therefore the dimension of this entire space is of size 2 to the D, right? And now a model, our models, will somehow, when it takes as input its plus or minus bit string, and map them to some real values, it will therefore represent some manifold or some subspace of this entire space of functions. In the case of a linear model, to be more precise, this will be a subspace because it's a linear model, right? And we can actually bound the dimension of the subspace in terms of the number of qubits on which this model acts on. And this is done essentially by a parameter counting of the space of functions that this model can represent. If you look at this linear model, right, you can essentially decompose an arbitrary observable O as a matrix of size 2 to the n times 2 to the n because it acts on n qubits, right? And then essentially you can decompose this function as a sum of this row of x taken as inner product with one basis vector of this entire space of observable, right? So you can essentially decompose a function like this as 2 to the n, 2 to the 2n, sorry, functions, right? Which all essentially are kind of linearly independent, right? So the dimension of this space of function has to be upper bounded by 2 to the 2n, because you can always decompose these functions as of the 2 to the n linear independent component, right? And then we have an upper bound on the dimension of this linear model. And then in the case of an implicit model, we are even more restricted on the structure of this observable O. When we have m data points, this O, this observable O that we take is spanned by m encoded data points, right? So it has a dimension at most m now, right? So it's even more restricted. The space is even more restricted because every observable can be decomposed as this linear combination of this m points, which do not need to be linear independent. But even if they were linear independent, it's still an m-dimensional space. And therefore, the dimension of this space for an implicit model is now upper bounded by the minimum between m and 2 to the 2m. It cannot be more than 2 to the m because it's still linear. And now, essentially, the argument is that if we want that our model has a good average performance on the entire functions in the space of all parity functions, this subspace needs to cover a big portion of the entire function space, right? And therefore, these dimensions have to be similar to each other, right? They have to be of the same order. And therefore, if you want your 2 to the 2n to be of the order of 2d, you need your n number of qubits to be of the order of d, the dimension of the input, right? And for an implicit model, on top of this requirement, you now need that the number of data points that you use from your training set need to be of the order of the 2d, 2 to the d, sorry. So it needs to be exponential, right? And this argument can be made rigorous, like visually it was this. This can be made rigorous by essentially using a theorem. It's very cool, right? So essentially, that's the pictorial way of visualizing why our linear models can be very much restricted by the number of qubits or the number of data points that they're using. This essentially has to do with the fact that they are linear. And then we can bound the dimension of their spaces they cover, right? This kind of visually the argument. I take a break for questions.
Would this argument works for other problems as well, or it's only for parity fitting?
So the argument works very well beyond parity, right? You just need that this dimension of the space, if the dimension of your space of functions of your concept class has a given dimension, right? Or for exponential in the size of your input, right? Then a similar argument will apply, right? So this argument really applies beyond parity functions, right? If your concept class is very large, then the number of qubits will have to scale logarithmically in the size of that function space, concept class. And then, yeah, the number of data points needs to scale linearly in the size, the dimension of that function.
Okay.
Okay, so now I showed you why linear models and implicit models are kind of restricted. Now, where does the power of data replotting models come in? Well, what we show is that there exists a data replotting model that acts on a single qubit, and with depth linear in the input dimension d, achieves a perfect learning performance on all parity functions. And this is actually a very simple and very cool circuit, data replotting circuit. So as a reminder, this are the functions we look at, right? We have a subset of the d-dimensional input, and we want the parity of some elements in that d-dimensional bit stream. So let's start with this circuit, where we start by just having a plus state, and then we're gonna do this z operations. These are parameterized by x, right? So we apply a z gate if x is 1. Or yeah, and we don't apply it if x is 0, right? Something like this. This x here, yeah. So essentially, if we start from the plus state, we apply this gate if z is 1. So we flip it if z is 1, and we keep it at the same. We keep it in the same state plus if x is 0. Then we look at x2, and we do the same thing. We flip it again if x2 is 1. We keep it the same if x2 is 0. And we'll keep on going like this until we've seen all the data points x1 to xt, all the components x1 to xt. And at the end, what we measure is if it's a plus or a minus state, right? We an x observable. And this will give us a label. And as you can see, this label will essentially encode the parity of the entire bit stream, right? We have flipped the bit between the qubit between plus and minus, depending on the values of x1 to xd. And at the end, what we get is the parity of the entire bit stream. But that's not exactly what we want. We want the parity of a subset. And here comes this very nice trick, where we essentially apply these RY gates that act essentially as Hadamards. They can act as Hadamards. So if we want that in our parity functions, this x1 does not appear, it does not contribute to the parity. So what we can do is apply a Hadamard on this plus state, turn it into a 0. Now the Z gate, right, will act as a global phase, right? We will keep 0 to 0 up to a global phase. So it will not contribute to that. And then if we apply Hadamard again here, we bring it back to plus. So essentially we hit the state of the qubit into this 0 state, such that the Z operation acts as a global phase, and then we bring it back to a plus. And now if you apply the second operation, now it will indeed contribute to flipping the plus to a minus or keeping it to a plus, right? And essentially by putting Hadamards wherever we want, we can hide the qubit from the applications of the Z operation parameterized by X. And essentially this is how we select which X's will contribute to the parity of our the final parity that we measured. So by properly selecting where we put Hadamards here, we can represent any of the parity functions that we want. And therefore, we have a single qubit data recording circuit that has a linear depth dimension. Yeah, depth linear in dimension that can perfectly represent any of this parity function. And yeah, that's how we get essentially our separations between data recording circuits, explicit models, and implicit models. Right. Now, the very cool thing is this result, this part of the result here, also tells us that if we come back to what we had before, we said that explicit models, right, can represent any data uploading circuits. But for that, we also need to add qubits. And now, what this result here, the separation that we have, a 1 versus d separation, the number of qubits, tells us also that the number of qubits we need to add to map a data uploading circuit to an explicit model must scale at least as the number of encoding gates that we had in our data uploading circuit. Otherwise, you will contradict with this lower bound that we find here. So essentially, we wrap around to what we started talking about at first about this mappings between data uploading and explicit models to show that, the overhead that we had earlier of this d log d is essentially optimal. Up to this logarithmic factor in d is essentially optimal, right? So we have a very simple argument wrapping back to this mappings from data uploading to explicit models. And that's it. That's my last slide just to give a take-home message that our results were essentially showing that all quantum machine learning can be expressed as linear models, right? And then we saw that explicit models can indeed have much better performance than implicit models when we look not only at training error, but at generalization error, right? So that's where quantum machine learning lies beyond kernel methods, right? We show this numerically, but we also showed rigorously that there are learning tasks where we can actually see a big separation between what explicit models can do and implicit models can do, but also what reaploading models add to the picture compared to explicit models. It's really these exact mappings have an overhead in the number of qubits, so it's not something that you cannot go around. And so the final recommendations, if you're looking for a recommendation of how to use quantum machine learning models in practice, it seems that data uploading can really have a very powerful model. Like as we saw, if you really design your data uploading model in a very task-specific way, like this parity function, you can really have a very flexible model that can accommodate for all the functions in your concept class very well. That would not be as easy with an explicit or an implicit model, right? The kernel methods as we see here can be very resource inefficient. They can require a lot of data to fit your data perfectly. And therefore, our final remark is that in quantum machine learning, not only the data encoding is important, course, how we encode the data into quantum state is very important. But this variational processing can really be a game changer, right? Like having an explicit model with a restricted variational termini can be very powerful, and having a very small manifold can be very interesting compared to a kernel method that has access to the full space, which can be a bit too large and lead to overfit. With this, I would like to thank you for your attention and welcome any questions.
Yeah, thanks, Sofiene, for a very informative talk. Yeah, like your last point basically connects nicely to our current train of research, right? Like people start looking into geometric machine learning, trying to exploit the structure of data in order to design our ansatz and data encoding metrics, data encoding gates for ansatz, so that we can reduce expressivities without like having a better generalization. And you already that show us a good examples about how like data reuploading circuit could like learn very well with parity functions by exploiting their structures, right? So one question that I have for you is that how many resources that you need to use to learn about the parity function in classical machine learning? Because like it's clearly that you can do very well with quantum by using data reuploading, but like, do you have any clue on how well the classical one doing?
Yeah, I mean, the papers that we really take our inspiration, not only inspiration, but also some results from, also show some learning separations with parity, on parity functions. In this case, for instance, in Daniel Barach, it's about neural networks versus linear functions, right? So in that case, what they managed to show is that rigorously they construct a neural network, classical neural network, that can also have close to perfect performance on learning these parity functions, right? Whereas they also show that a linear model will perform very badly, right? A classical linear model will need essentially exponentially large feature spaces in order to learn, or a lot of data points as we saw, in order to learn this parity functions easily. So there is a catch here, is that yeah, you need to have a very special input distribution in order to make this learning efficient for neural networks, or even for, in our case, in order to make this learning efficient, we also need a special distribution on this input data. If it's a uniform distribution and you put some noise in, it becomes actually quite hard to learn parity functions. Right? They are very sensible to noise. This comes back to an argument about SQ learning, spec learning stuff from Kearns. Actually, it becomes parity functions are tricky to learn on the uniform distribution when there is no noise whatsoever. They are very easy to learn. And in practice, when you train a neural network, for instance, this is kind of a noisy training that makes, again, learning parity functions very hard on the uniform distribution. But you can still kind of cheat a bit and then have a distribution that's a bit more revealing of what parity function you have, which will keep the same lower bounds, similar lower bounds for linear functions. They will still have a hard time learning even under the distribution. But for classical neural networks, it becomes easy, and it also becomes similarly easy for our reuploading and explicit models. They can use very little data in order to learn these functions. So yeah, parity functions are not the quantum advantage.
Yeah, of course. I'm just wondering like how like the classical machine learning people just deal with it, right? Yeah.
Yeah. So they're still learnable. Like with this little tricks, of course, the same tricks that they use, and they manage to learn them with neural networks. Like,
is it like when you look at this problem, is it trivial for you to come up with the data reuploading circuit that perform this well, or you have to really stay on the problem a bit in order to get that circuit out?
To get this data reuploading circuit.
Yeah. Is it natural to you, like when you look at the problem itself? Yeah.
I mean, for me, it was really seeing this trick that I can hide information out of the equator of the block sphere. Essentially, I can hide it here, such that the z rotations act as global phase. Right? For me, this was the click that made me think, okay, one qubit data reuploading circuit is actually very, very powerful and can do things.
Yeah,
In a general task, yeah. In a general task, I could not give you recommendations on how to design a data reporting circuit.
Of course.
I think, as you say, the work on geometric deep learning is kind of trying to, give some recommendation on how to design data reporting circuits and really exploit the symmetries of your problem. And that's definitely a very cool direction to go into right now. But yeah, other than that, I don't have much recommendations of how to build a data reporting circuit.
It's quite cool that you now be able to come up with this like hiding information trick that might be useful for some other like machine learning algorithms. Yep. It seems like we didn't have question from the audience. I guess that maybe they have to take time. They need some time to digest like the informations, and like if they have questions, I think that there will be maybe like send you a message or like email to ask about.
I'll be very happy if anybody wants to send me an email. They can find it.
Actually, I do have a few questions, but it would be technical. So I think it should be better to like take it offline, and we can like find time to like chat more about it.
Definitely.
Yeah, I guess like it's overshot by quite a bit, but it's like very informative and interesting talk. So I guess we can thank Sofiene for all the interesting talk, and like hope you can like come up with new work like in the futures, and then we can just like have you back in our seminar again. I will record like upload these videos and then put on YouTube and let people like kind of watch it, because like maybe there some like they just clash in their schedule. Thanks again like Sofiene for accepting to talk in our seminars. And
thank you.
Thank
you for inviting me. Thanks for all the questions, and take care. Bye-bye.